Dear learner, welcome to this video lecture of Module 11 on Semiconductor Devices of the online course on Electricity and Electrical Wiring. I am Dr. Antara Mohanto Borua from the discipline of Electronics, Krishnakanta Handike State Open University, Guwahati. This is the fourth lecture of Module 11, which is on integrated circuits and its applications. In the previous lecture, we have discussed about transistor and its applications. In this lecture, we will focus on basics of integrated circuits, then types of integrated circuits. In case of analog integrated circuits, we will learn about the operational amplifiers, then applications of operational amplifier, or in short, op-amp. Then we shall learn about the voltage regulator integrated IC, after that timer IC, and in the last we will discuss the logic gate integrated circuits. So the main objectives of this lecture are to provide an overview of the integrated circuits, introduce and highlight the significance of the operational amplifier, then describe the various applications of the operational amplifier. After that, to comprehend the uses of voltage regulator integrated circuits, then to get an idea about the timer ICs and also about the various types of logic gate integrated circuits. So with these objectives in mind, let's begin with what is an integrated circuit. So an integrated circuit is a set of electronic circuits in which both passive and active components are fabricated on a small flat piece, or you can say chip, of semiconductor material. A large number of components such as resistor, capacitor, diode, or transistors are embedded into a single silicon wafer using photolithography and other microfabrication techniques. These components are isolated from each other by isolation diffusion within the crystal chip and are interconnected by a layer of aluminum that serves as wire. It can be used as amplifier, oscillator, timer, microprocessor, or memory module. On the other hand, in a discrete circuit, all the components are produced separately and then assembled to form a complete electronic circuit. J.X. Kilby of Texas Instruments was the first person to develop an integrated circuit chip. Now, what are the advantages of integrated circuits? Integrated circuits offer significant advantages over traditional discrete circuits. These are small size. ICs allow for much smaller circuit designs compared to discrete circuits, which results in saving space within the electronic devices. So next advantage is lightweight. Due to their compact design and reduced component, ICs based circuits are lighter than the equivalent discrete circuits. Low power consumption. Because of their small size, ICs are more suitable for low power consumes compared to discrete components. So next advantage is reduced cost. This is one of the major advantages of integrated circuits. The reduction cost per unit is due to the fact that many identical circuits can be built simultaneously on a single wafer. High reliability. With fewer interconnections and soldered joints, integrated circuits are less prone to circuits failures. Small temperature rise due to low power consumptions of ICs also improves their reliability. Faster performance. Short distances between components make the ICs faster to operate. Though there are lots of advantages of integrated circuits, it suffer these drawbacks. So the first is, after fabrications of an integrated circuit, it is not possible to modify the parameters within which an IC will operate. When a component of an IC gets damaged, the whole IC has to be replaced by new one. The inductor coils cannot be fabricated. They can handle only limited amount of power and they function at low voltages. So dear learners, now let us move to the next topic, that is the types of integrated circuits. So ICs are of two types based on their method of construction. So first is the analog integrated ICs and then the digital integrated ICs. So analog integrated ICs are also referred as linear integrated circuits because they deal with continuous signals. That means their input and outputs can take on a continuous range of value and the outputs are generally proportional to the inputs. So for example, operational amplifier, that is op-amp, and the voltage regulators. So let us see the operational amplifier IC741 pin diagrams. So this is the pin diagrams. Here pin 1 is represent offset null. Pin number 2 and 3, that is the inverting input and the non-inverting input terminal, and output is taken at pin number 6. 7 is the positive bias supply and pin 4 is the negative bias supply, and pin 5 is the offset null which is not used, and the 8 is the not connected, it is remain free. IC741 is an example of linear integrated IC. So next, digital integrated ICs. So the digital integrated ICs are deal with binary signals, that is 0 and 1. Examples are logic gates, microcontrollers, microprocessors, memory chips, etc. So now, what is op-amp or operational amplifier? So the operational amplifier is a very high gain directly coupled negative feedback amplifier which can amplify signals having frequency range from 0 Hz to around 1 MHz. The op-amp is shown as a triangular symbol in the circuit and having 2 inputs and 1 outputs. The 5 terminals in the configuration of op-amp are: number 1, inverting input terminal, non-inverting input terminal, output terminal, positive bias supply terminal, and negative bias supply terminal. I have already told that the IC741 is one of the most widely used integrated circuit for operational amplifier. Now, characteristics of operational amplifier. So the important characteristics or parameters of op-amp are as given here. So first characteristics of op-amp is the open loop voltage gain. Then second one is the output offset voltage, common mode rejection ratio, and slew rate. So now let us discuss these characteristics in detail. First is open loop voltage gain. So open loop voltage gain of an op-amp is its differential voltage gain without any feedback path. That means the loop, there is no loop, it is open, so there is no feedback. And mathematically, the open loop voltage gain of an op-amp is represented as within this formula, this equation, AV equal to V0 divided by V1 minus V2. So next is the output offset voltage. The voltage present at the output of an operational amplifier when its differential input voltage is 0 is called as output offset voltage. So next, common mode rejection ratio. So common mode rejection ratio of an op-amp is defined as the ratio of the closed loop differential gain, that is AD, and the common mode gain AC. So the closed loop differential gain of the op-amp is the gain of the op-amp means when the feedback is applied and the input is a differential signal, that is the voltage difference between the inverting and non-inverting inputs. So mathematically, common mode rejection ratio can be represented as AD divided by AC. Now you note that the common mode gain, that is AC, is the ratio of the common mode output voltage and the common mode input voltage. And the next characteristics is the slew rate. So slew rate of an op-amp is defined as the maximum rate of change of output voltage due to a step input voltage. And mathematically it is represented as slew rate is the maximum of DDT V0. That is, V0 is the output voltage. And in general, the slew rate is measured in volt per microsecond. If we change in the or increase one step in the input, what is the maximum change in the output is represented as the slew rate. Now, the op-amp are basically two types. One is ideal op-amp and the other is practical op-amp. Now, we will discuss them now. The ideal op-amp generally it does not use in the practical purpose. It is only theory, and the equivalent circuit of ideal op-amp is shown here in the figure. And the characteristics of the ideal op-amp are the input impedance is infinity, that is Zi is infinity. The output impedance Z0 is equal to 0 ohm. Open loop voltage gain AV is infinity. And the input voltage Vi is equal to 0. Then the output voltage will also be 0 volt. Next characteristics is the bandwidth is infinity. So it means that an ideal op-amp will amplify the signal of any frequency without any attenuation. So common mode rejection ratio is also infinity in case of ideal op-amp. Slew rate is infinity. It means the ideal op-amp will produce a change in the output instantly in response to an input step voltage. The practical op-amp. The equivalent circuit of the practical op-amp is shown in this figure, and it exhibits the characteristics. Number one is the input impedance, that is Zi is very high in the mega ohm range. Then output impedance Z0 is low. It is in the order of few ohms. Open loop voltage gain AV will be very high. Output voltage should be very low. The operating bandwidth should be very high in case of practical op-amp. Common mode rejection ratio is also should be very high as possible. Slew rate should be high as possible. Now, what are the applications of operational amplifier? So, op-amps can be used in both linear and nonlinear applications. When the linear relationship exists between these input and the output voltage of the circuit is said to be linear. Similarly, the circuit is said to be nonlinear if there is a nonlinear relationship between its input and output. So the basic applications of operational amplifiers are inverting amplifier, non-inverting amplifier, and voltage follower. So let us discuss first what is inverting amplifier. An inverting amplifier takes the input through its inverting terminal through the resistor R1, and it produces its amplified version as the output. This amplifier is not only amplifies the input but also it inverts. The circuit diagram of an inverting amplifier is shown in this figure. And you note that for an op-amp, the voltage at the inverting input terminal is equal to the voltage at its non-inverting input terminal. So physically there is no short between these two terminals, that is inverting and non-inverting, but virtually they are in short with each other. In this circuit, the non-inverting input terminal is connected to the ground. That means 0 volt is applied here. Now, according to the virtual short concept, the voltage at the inverting input terminal will be 0 volt. So the ratio of the output voltage, that is V0, and the input voltage Vi is the voltage gain or gain of the amplifier. Therefore, the gain of the inverting amplifier is equal to minus Rf by R1. So go through these equations where Rf is the feedback resistor and R1 is the input resistor. The gain of the inverting amplifier is negative. That means there exists a 180-degree phase difference between the input and the output. Now, non-inverting amplifier, it takes the input through the non-inverting terminal and produces its amplified version as the output. As the name suggests, this amplifier just amplifies the inputs without inverting the output. The circuit diagram of non-inverting amplifier is shown here. The input voltage Vi is directly applied to the non-inverting terminal, that is the positive terminal of the op-amp. So the voltage of the positive terminal will be Vi. Now, by using the voltage division principle, we can calculate the voltage at the inverting input terminal of the op-amp as shown here. Now, as we already discussed that according to the virtual short concept, the voltage at the inverting input is same as the voltage of the non-inverting input. Now, the ratio of the output voltage V0 and the input voltage Vi, or the voltage gain or the gain of the non-inverting amplifier, is equal to 1 plus Rf by R1, where Rf is the feedback resistor and R1 is the resistance applied to the inverting terminal. Note that the gain of the non-inverting amplifier is having a positive sign, so it indicates that there is no phase difference between the input and the output voltage. So the next application is the voltage follower. So a voltage follower is an electronic circuit which produces an output that follows the input voltage. It is a special case of non-inverting amplifier. If we consider that the value of the feedback resistor, that is Rf, as a 0 ohm, the value of the input resistor R1 as infinity ohms, then a non-inverting amplifier becomes a voltage follower. So this is the circuit diagram of the voltage follower. In this circuit, the input Vi is directly applied to the non-inverting terminal. Here the output is directly connected to the inverting terminal. Hence, the voltage at the inverting input terminal of the op-amp will be V0. Now, according to the virtual short concept, the voltage at the inverting input terminal is same as the voltage at its non-inverting input terminal. So, therefore, V0 equal to Vi. So, the output voltage V0 of the voltage follower is equal to the input voltage. Thus, the gain of the voltage follower is equal to 1. These three are the basic applications of the op-amp that comes under the linear operations of the op-amp. So, op-amp can also be used in the electronic circuits which performs arithmetic operations, and these circuits are called as arithmetic circuits. Using op-amps, you can build basic arithmetic circuits such as adder and subtractor. So in this session, we will just learn about what are they, and we will not go through the details of the calculations. So first is adder, and adder is an electronic circuit that produces an output equal to the sum of the input voltages applied to its inverting terminal. It is also called as a summing amplifier. This is the circuit diagram when op-amp is used as an adder. In this circuit, the non-inverting terminal of the op-amp is connected to the ground. That means 0 voltage is applied to the non-inverting terminal. And as according to the virtual short concept, The voltage at the inverting terminal is same as that of the non-inverting terminal. So the voltage at the inverting terminal will be 0 volt. And the equations for the adder is given here. The op-amp based adder circuit will produce the sum of the two inputs voltages, that is V1 and V2, as the output when all the resistors present in the circuit are same value. And note that the output voltage V0 of an adder circuit is having a negative sign. That means what? There is a 180-degree phase difference between the input and the output. So the equation for the adder circuit is output voltage V0 is equal to minus V1 plus V2. So next is subtractor. A subtractor is an electronic circuit which produces an output which is equal to the difference of the input voltages applied to its inverting and non-inverting terminals. It is also called as difference amplifier since the output is an amplified one. The op-amp based subtractor circuit will be produced an output which is the difference of the input voltages V1 and V2 when all the resistors present in the circuit are of same value. And the equation for the subtractor circuit is V0 equal to V1 minus V2. Now next applications of arithmetic circuit is the differentiator. So the circuit which performs mathematical operations such as differentiation, integrations are called differentiator and integrator circuit. So a differentiator is the circuit that produces an output equal to the first derivative of its input. An op-amp based differentiator produces an output which is equal to the differential of the input voltage that is applied to its inverting terminal. This is the circuit diagram for differentiator. In this circuit, the non-inverting terminal of the input is connected to the ground. That means 0 volt is applied in the non-inverting terminal. The feedback element is the resistor and the input component to the inverting terminal is the capacitor. Now, according to the virtual short concept, since the non-inverting terminal voltage is 0, therefore the inverting terminal voltage is also considered as a 0. So the voltage at the inverting terminal is 0 volt. So the output voltage of the differentiator circuit is V0 is equal to minus ddt of Vi, whereas Vi is the input voltage applied to the inverting terminal. So these waveforms are the input-output voltage waveforms for the differentiator. When input is sinusoidal, there is a phase difference in the output voltage. Integrator. So an integrator is the circuit that produces an output, that is the integration of the applied input. An op-amp based integrator produces an output which is an integral of the input voltage applied to its inverting terminal. This is the circuit diagram for the integrator. And in this circuit, the non-inverting input terminal is connected to the ground. That means 0 volt. And similarly, according to the virtual short concept, the voltage applied to the non-inverting terminal is also considered as 0 volt. This is the equation for the inverting input terminal in case of integrator. And the output voltage of the integrator circuit is V0 equal to minus integration of Vi dt. In case the feedback element is capacitor and the input component is the resistor. This is the input-output voltage waveforms for integrator circuit. When input is square wave, the output is the triangular. There is a phase difference. And in case when the input is the sinusoidal, the output will be cosine wave. Next is the comparator. So a comparator circuit is the circuit which compares the two inputs that are applied to it and produces an output. The output value of the comparator indicates that the input is greater or lesser. Please note that the comparator falls under the nonlinear application of integrated circuits. This is the circuit diagram of an inverting comparator, and the operation of an inverting comparator is very simple. It produces one of the two values, that is plus V set and the minus V set at the output based on the values of its input voltage Vi and the reference voltage VRF. This is the input-output waveform for of an inverting comparator when the reference voltage is 0 volt. So dear learner, after discussing the basics of integrator circuits, operational amplifier and its applications, let us now go through a small quiz to test our understanding. I hope you were able to answer these questions. Now let us move to the next topic, that is voltage regulator integrated circuits. It is commonly used in power circuits where the output should remain constant irrespective of varying input voltage. These ICs ensures a constant output. Now classification of ICs, that is voltage regulators. Now, according to the pin type, voltage regulator IC is classified as multi-pin type. For example, LM723C, and 3-pin type, for example, 78 or 79XX. So, this is the nomenclature of the voltage regulator IC. So, it can also be classified as fixed voltage regulator and the adjustable voltage regulator. So a fixed voltage regulator can be positive voltage regulator or a negative voltage regulator. So positive fixed voltage regulator provides a constant output voltage. All those ICs in the 78XX series are fixed positive voltage regulators. A popular example of it is 7805 IC, which provides a constant 5 volt output. In the IC nomenclature 78XX, this is the XX parts denotes the regulated output voltage of the IC. For example, 7805, 7806, 7809, etc. are the positive fixed voltage regulator IC. Now, a negative fixed voltage regulator is same as that of the positive fixed voltage regulator in design, construction and operation. The only difference is in the polarity of the output voltage. These ICs are designed to provide a negative output voltage. For example, 79, which the series which starts with 79, that represents the negative output voltage. So example 7905, 7906 and all those ICs in the 79XX series All are negative output voltage regulator ICs. So next is the adjustable voltage regulator. It is a kind of voltage regulator whose regulated output voltage can be varied over a range. There are two variations. One is the positive adjustable voltage regulator and the other is the negative adjustable regulator. So IC LM317 is an example of positive adjustable voltage regulator whose output voltage can be varied over a range of 1.2 volts to 57 volts. LM337 is an example of negative adjustable voltage regulator. The only difference is that the polarity of the regulated output voltage. So now we move to the next topic, that is the timer integrated circuits. So it is used to create time delay, pulse generation and oscillator applications. One of the popular timer IC is 555 timer or 555 timer. The pin diagram of the 555 timer IC is shown here, where it has 8 pins mini dual inline package. This is the IC for 555 timer. Now the pin diagram for the timer IC, 1 represents ground, 2 is trigger, 3 output, 4 is reset, 5 is control voltage, 6 pin represents threshold, 7 is discharge and 8 is the supply voltage. This IC can be operated with a DC power supply of plus 5 volt to plus 18 volt. It is mainly used for generating non-sinusoidal waveforms. This is the waveform for timer ICs like square, triangular, sawtooth or ramp, etc. The 5 internal components present in the 555 timer IC are voltage divider, comparator, RS flip-flop, transistor and out buffer. So out buffer is a temporal storage. So RS flip-flop is also known as set reset flip-flop that can store a single bit of information, and it has 2 stable states, or it can call a bistable multivibrator. It works based on the 2 inputs which are controlled by the output. Now some of the applications of timer ICs are: it is used in the microprocessor, microcontroller, counter, in transducer, data acquisition, starting and ending industrial processes, traffic lights, etc. So next we'll move to the logic gate integrated circuits. So logic gate is an digital integrated circuits which works according to some logical relationship between the input and the output voltages. A logic gate may have one or more inputs, but it has only one output. The relationship between the values of input and the output voltages are expressed in the form of table which is called truth table. The basic logic gates are: number 1 OR gate, then AND gate, NOT gate, XOR gate, XNOR gate, etc. These are the relationship and the truth tables of various gates. So I will not go through in details in this lecture about these logic gates. Now let us see the list of the logic gate integrated ICs which are used in simulation purpose. So first is IC 7404, that is the NOT gate IC. Then IC 7432, it is the 2-input OR gate IC. IC 7408 is the 2-input AND gate IC. IC 7400, it is the 2-input NAND gate. IC 7402, it's 2-input NOR gate. IC 7486 is the 2-input XOR gate. IC 74266 is the 2-input XNOR gate. Now for 3-input terminals, the IC 7411, it is the 3-input AND gate. IC 74H C4075. It is the 3-input OR gate. And 3-input NAND gate IC is 7410, and 3-input NOR gate IC is 7427. So dear learner, it is now a time for a self-check of what we have learned about the voltage regulator ICs, timer IC, and logic gate ICs. Please attempt some multiple choice questions to test your understanding. So we have come to the end of today's session. In this lecture, we have started with a discussion on the integrated circuit, how it is classified. We have also learned about the operational amplifier and its applications as linear amplifier and arithmetic circuits. Finally, we have discussed about the voltage regulator ICs, timer ICs, and logic gate ICs. For further reading, you may refer to these reference materials. So thus we come to the end of this video. Thank you.